Hey kids, time to move on from just regular series, right? We've started with sequences, then we went to a series, and now we're going to talk about a special kind of series called a Taylor series. Now, this is Brooke Taylor. He was an English mathematician from 18 something, I don't know, but he's the one that developed the Taylor series. You're going to be doing a lot with Taylor series next year in BC Calculus. I will teach you how to construct a Taylor series next year. You do not need to know how to do that now. We are just going to take a few common functions and I will give you the result of Brooke Taylor's work and the power series that represents some functions that you already are pretty familiar with. And next year, I'll teach you how to build a Taylor series representation for any function. So let's start off with some numeric series, right? One of the last tests we learned to see if a numeric series will converge is using the ratio test. And our clue to use the ratio test was that we had powers and factorials. So can you just kind of look and predict if these will converge? What do you think? Right? And I'm not expecting, it's a 50-50 shot. Yes, they will. No, they weren't. No, they won't. So let me set up the ratio test, right? The ratio test is the limit as the n goes to infinity, right? And I told you to slap an absolute value, though you don't really need it on here. And you want to know if this limit is less than 1. For convergence, greater than 1, you'll get divergence, and equal to 1, inconclusive, right? And I taught you how to put in your n plus 1s. And divide by the previous term, but doing that means you are multiplying by the reciprocal of the previous term. I taught you how to do exponent work with this, right? So you know nothing's going to happen to the n factorial and the what's going to happen is you're going to end up with n plus 1 times n factorial, so those are going to go away. This is going to be 3 to the n times 3 to the first. This 3 to the n is going to go away, so you're going to end up with a 3 here. So the limit as the number of terms goes to infinity is looking like the limit as n approaches infinity of 3 over n plus 1, which is bottom heavy, so that this limit is 0. 0 is indeed less than 1, therefore converge. Right? This numeric series will converge to a sum. I can't find that sum, but I can tell you that it will converge to a sum. That, right? If you keep adding those terms as you go off to infinity, the factorial is going to overpower the 3 to the n. So can you predict what will happen if I have a 10 instead of a 3? Right? Isn't the same thing going to happen? Right? I'm just going to end up with a 10 over n plus 1, which that limit as I go to infinity is going to be 0. All right, so little numeric series review with the ratio test. Instead of asking you to predict, though, what if I just said, I'm not going to tell you what that number is. I'm going to hide the number from you, right? I'm going to say it's just x to the n over n factorial, right? Kind of sneaky, right? Well, what if x was 3? So if I give you this series and I say, but when x is equal to 3, what does the series look like? Well, it looks like that. What about when x is equal to 10? What does the series look like? Well, it looks like that. Oops, sorry about that. So all I'm doing is giving you a numeric series, but I'm replacing the number there, 3 and 10, with x. So I can't call it a numeric series because I don't know the number that you're putting in for x. So I'm going to call it a power series. Whoa, I've got the power, right? It's a power series because I have the power of hiding the number that I want you to take to the n and divide by n factorial. Substituting numbers in for x creates a numeric series, and then I can test that numeric series and see if I get convergence, right? But the power of representing the number 3 or 10 with an x is that I can now ask you lots of, what about when x is, right, 7? In other words, I can ask you to input a number and you can output a numeric series. I feel like that's kind of function talking, right? Input, output. Curious. So for a given x, if x is 3 or x is 10, for example, will the power series, which will then become a numeric series as soon as you plug in for a number for x, converge? But what if I just want to know in general, right? I don't want to say for x is equal to 3 and x is equal to 10. I want to test if the power series x to the n over n factorial will converge for any x. So look at what I'm going to do. I'm going to use the ratio test. I'm going to use the ratio test, and I'm going to take a limit as n goes to infinity. And again, I'm going to throw these absolute value bars around here, and I'm going to say the same thing. Will that limit be less than 1? Now I need you to pay attention here. I'm taking the limit as n goes to infinity. Here are my n's. I am not taking a limit as x goes to infinity. So your job is to first job is to get x out of the situation. Whoops, sorry. So what I'm going to do is I'm going to do some extra rewrites here, unlike I did when I was just doing a numeric series. So, but I'm going to do something very similar, right? I'm going to say the limit as n approaches infinity I'm not going to deal with these factorials yet. But my x, I'm going to do this. X, oops, I didn't want white, did I? X to the n times x to the 1 over x to the n. You're not shocked by that scenario, right? That happened with the numeric series. But now I just have an x to the first. And I'm going to be taking a limit as n approaches infinity and checking to see if this is less than 1. Well, let me remind you of some properties of limits we did way back. Since x is not involved in the situation, I'm going to osmosis the x part out front and let me just work with the limit as n approaches infinity. Now, the x, and this is why I always told you to plop those absolute value bars around there. Right? X was inside absolute value, so keep it. And then copy over everything else to do with the limit. Evaluate this limit. Do you remember what this is going to go to? Right, I'm going to have n over just doing the blue limit part. What is this? Whoops, cancel those out. So I have 1 over n plus 1, bottom heavy. Where does this limit go? This limit goes to 0, but here's the extra piece from Brooke, our power. You can't forget that a power series involves x. You had the absolute value of x times all of this, times the limit. So you have the absolute value of x times 0, which is less than is that less than 1? And you're asking for what values of x will this statement be true? When will this statement be true? When is the absolute value of any number times 0 less than 1. Any number, okay? So let me see. How about 0? Is the absolute value of 0 times 0 less than 1? Yes. How about 10? Is the absolute value of 10 times 0 less than 1? Yes. How about 3? Is the absolute value of 3 times 0 less than 0? Yes. How about negative 30? Is the absolute value of negative 30, which is 30 times 0 less than 1? Yes. So this statement, when is this statement true? For what x's? For any x ever. Any x ever. So our original statement, the power series, remember the power series we got from Brooke. You don't know how it was built, but here's what we got. X to the n over n factorial. Good thing that 0 factorial is defined as 1, right? That was our power series, right? Because it had an x in it. That you can replace this x by doing the ratio test with the x's in it. You can now say that you can put any x in there and you will get a convergent power series. You don't need to do the ratio test for every series. When x is equal to 3, when x is equal to 10, when x is equal to negative 30, you don't have to test it because you tested it for every x. For every x, and you did the ratio test with x in it, and you got for every x, you can replace any x in the universe here, and you will get a convergent numeric series. And remember, you don't know why you will love convergent numeric series, but you do. Since that from the ratio test, right, that r, which I like to call capital R, will always be equal to 0, which is always less than 1, regardless of what x happens to be. The original power series will converge no matter what x you put in, and you don't have to run another test on it. So since we are using x as input values, I'm going to use function notation. And I'm going to say f of x is equal to that infinite series. And further, for no matter what x you put in, that's a comma, which will create a convergent numeric series for any x you put in. For any x you put in. That's freaking crazy. All right, so what? All right, let's go back to the original and expand the summation formula and see what some of the terms look like, okay? So in other words, I just want you, here's f of x. So what does expand this out? What does it look like? When n is equal to 0, I have x to the 0 over 0 factorial. Plus, when n is 1, I have x to the first over 1 factorial. Well, when x is 2, I have x squared over 2 factorial. When x is 3, hey, well, wait just a gosh darn second here. Something to the 0 is 1, 0 factorial is 1, so that's 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4th plus what is happening? What is happening? That is a freaking polynomial. It's an infinite polynomial. And you know what you know? A lot of freaking stuff about polynomials. You know how to deal with polynomials. There's a lot of things you know how to do with polynomials. Oh, snap. Well, then if I can input any x, what can I put in? I can put in 1. I can expand it. I can get a rule for it. I don't need to know. I don't need to test this numeric series to see if it converges. 1 to the n over n factorial converges by the ratio test because I can put any x in and get a convergent numeric series. Now, I can't find an infinite sum. And it's not like next year I'm going to be like, remember when I told you couldn't find an infinite sum in that series? Well, no. But I can find some partial sums, can't I? So you might not know why I'd want to do that, but what if I want to know what f of 1 approximately is. So I can't plug 1 into this series and get an actual sum, but I can cut it off here, right? I can cut it off right there and add all those up. That's not that hard, right? So this is the polynomial 1 plus 1 plus 1/2 times 1 squared plus 1/6 times 1 cubed, right? That's not hard to do. Why don't you get out your calculator? If you get out your calculator and you look at these things, right? You look at these numbers, and I'm just going to plug them in. I'm going to stop the infinite. I'm going to make it finite. So f of 1 is not equal to, it is approximately equal to when I plug these in, and I have 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. Add all those up. You're going to get 2 point something, aren't you? Let's see, I wrote it down and I got 2.6666. So 2 and, not surprising, 2 2/3, right? Okay. Well, what if I want a better approximation for f of 1? Think about that finite polynomial. I cut it off, didn't I? Where did I cut it off? I cut it off after 3 terms. What if I cut it off not after 3 terms? What if I cut it off after 5? So how am I going to do this? This is going to be 1 plus 1 plus 1/2 plus 1 over 3 factorial, right? Because I'm plugging, right? Plus 1 over, that was 3 factorial, 4 factorial was 24, plus 1 over 1/20th. What is that? Let's see, I wrote that down. What did I get? I got 2.7. 1666. Okay, whatever that is. Remember, f of 1 isn't exactly this. F of 1 is approximately because I stopped it. It's not going to infinity. Right? What about, oh my goodness, this is just getting, right? This is getting, why do I care? All right, I'm not going to write this out, but I am going to write, I can see, I wrote down what I got for this. So I did all this, and I got 2. That doesn't surprise me. 2.7, and then I got the 1, and then I got an 8, and then a 2, and then an 8. Oh, hey, do you remember that Andrew Jackson was president in 1828? Andrew Jackson, probably the worst president of all time until lately. And I don't mean current president. 1828. Oh, that's funny. That repeats Andrew Jackson. And then I got a 9. 5. Hey. I'm sorry, I got a 45 and a 9. Wait, what? 2.7, Andrew Jackson, and did you know window wipers used to, in old times, click from 45 to 90 degrees to 45? What is happening? When I get, wait a second, you know what that number is really close to? Naturally. Hello, Andrew Jackson. E to the first, right? Remember, this is e to the first. That's what I got. What, did you see it coming? You didn't see it coming, did you? This function, this infinite series is e to the x. What is happening in my life right now? I don't even know. My world is blown apart. Whoa. Mind blown. Somebody, when you first start introducing E in Algebra 2, and then you're like, wow, who calls it a natural number? Well, it came naturally out of exploring this numeric series that I just hid the number and I called it X and I plugged it in. I got an infinite polynomial. I started plugging in numbers, cutting it off infinite, and oh my God, when I kept plugging in numbers and summing them, I got E. What is now? This is so cool, right? I guess, but why do I care? So let's look at, I'm going to take you to, there's a link when you have this PowerPoint, there is a link here to Desmos. So let's look at what we've got over here. Now I want you to remember that when I plugged in, right, when I started expanding this, I got for n, not for x, when I started expanding for n, I got 1 plus x to the 1 over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... Thanks, Brooke. I got that infinite polynomial. So I want you to look at this graph here, and I want you to realize what if you stopped this infinite polynomial after the first term, stopped it here, you would get f of x is equal to 1. There's that graph, f of x is equal to 1. So I have here f of x is equal to 1. I've truncated the infinite polynomial after one term. I've also graphed the function e to the x. Does the green function look at all like e to the x? No, it doesn't. Well, it does at one place, right here. They look exactly the same. But how about if I said, well, I'm gonna cut off that infinite polynomial after the second term. Hey, they match a little bit right there. What if I put another term? Oh, hey, look. The truncated polynomial is matching E, a little bit bigger radius there, right? Gee, I wonder what happens if I add another term. Hey, and another? What? Do you see the radius around that middle, right? Where they first were at 0, 1? Do you see that the functions are matching for a larger and larger radius? Do you remember when we did the ratio test? What did we say about how many numbers you can plug in? An infinite. Any x you can plug in and you will get a convergence. Do you see the polynomial converging to the polynomial graph converging to the graph of e to the x? I mean, it's freaking beautiful. That is cool. It's pretty cool. So if I can't graph this infinite polynomial. I can't plug in to this infinite polynomial, but I can get I can get a lot of functions and a lot of numeric series that are super close to e to the x. So what do I care? Let's use the first 6 terms to approximate e to the x. What x do I want you to plug in? I want you to plug in 0.2 for e to the x. So I want the first, hey, why is that not a 6? Why is it a 5? Oh, right. They said 6 terms, but remember, this is the first term, 1, 2, 3, 4. So this is 0.2 right? This is plug 0.2 in for x. 1, there's x to the 0, right? Plus 0.2 plus 0.2 squared over 2 factorial, which, yes, is just 2, plus 0.2 cubed over 3 factorial. 1, 2, 3, 4. Didn't leave myself enough room there. So that's 1, 2, 3, 4, 5, 6 terms, and my n stopped when it was 5, right? I can put that into my calculator and I can get an approximate. And I wrote it down and I got, probably wondering why I care, 1 point, well, there's gonna be a really cool thing here, 1.221402667. Notice I didn't ask you to do this yourself, but you could. Right on my home screen, I could just type all this up, right? But I don't want you to do that. Instead, I do want you to get your calculator, so if you don't have it, go get it. Go to your calculator, and I want on your calculator, on your home screen, I want you to say e to the 0.2 and tell me what your calculator says and tell me that your mind isn't blown. What? E to the, where do you think your calculator is getting this information from? E is a never-ending, non-repeating transcendental number. How do you take that number and raise it to the 0.2? Hint, you don't. You approximate it with a polynomial. And your calculator gives you 1.22140, and then it diverges because you truncated the polynomial. You couldn't plug 0.2 into the infinite polynomial. But you know what? Being accurate to that many decimal places is pretty freaking good. What do you think your calculator is programmed with? Right? I mean, that is really cool. That is your first famous Taylor series. Thank you, Brooke. Okay, so special Taylor series. There are lots and lots of Taylor series, but there's a list of specials, and this is at the top. And you have known about the function e to the x for a long time, but did you know that e to the x is actually an infinite polynomial that is built from the series x to the n over n factorial? What now? Let's investigate a couple of others. Oh, my Lancet, look at that. All right, don't freak, right? Use your factoring brain. I have a sign alternator. Here's my x that I'm plugging into. So this is a power series. And then I have a factorial in the bottom. Now what, I know when I have a power. Oh, and they match. Look at that, right? The powers match here. 2n plus 1, 2n plus 1 factorial. What is 2n plus 1? What kind of number is that? When you plug in 0, when you plug in 1, when you plug in 2, when you plug in 3, what kind of values do you get out of that? Right, odd numbers only, right? So the terms of your series are all going to be odd, and you're going to be dividing by odd factorials. So if I asked you to expand this out, you could. And that's what it looks like. Plug in 0, negative 1 to the 0 is 1, so that's positive. X to the 2 times 0 plus 1 is first, so that's x to the first, over 2 times 1 plus 0, 2 times 0 plus 1, which is 0 plus 1 factorial, which is 1 factorial, right? And then your signs alternate, and you only have the odd powers. Here's another one. I have a sign alternator. Here's my power series. And then n starts at 0, and what does n do? This time the power on x and the factorial also match, but what are they? They're not odd powers. What are they? Even. So write out a couple terms of that. So plug in 0, negative 1 to the 0 is 1 to the 0, which is positive, right? X to the 2 times 0, which is x to the 0 over 2 times n, which is 0 factorial. So this is x to the 0 over 0 factorial, which is 1. Then my signs alternate, and I have, and really you have an x to the 0 here, and 0 is an even number, right? That's kind of a cool pattern. Hey, let's go back. Let's graph some of these terms and see if we see, I wonder if this graph converges to e to the x. Hint, it's not going to. We already know what infinite polynomial series converges to e to the x. I'm going to leave e to the x up there, but I'm going to put in, remember what the first term was? X, right? And then what was the second term? Signs alternated, and I had x cubed divided by 3 factorial, right? Now, hopefully you're not surprised to see that's a cubic, right, with a negative leading coefficient. You're not surprised at the end behavior of that. And then I added x to the 5th over 5 factorial. That's also an odd degreed polynomial, so that you're not surprised, but with a positive leading coefficient, so you're not surprised, right? Let's do another one. Minus, right, because the signs alternate, x to the 7th, 7 factorial. Let's look at what that looks like. Let's do another one. Again, hopefully you're not surprised, at the ends anyway. Hey, that green graph certainly isn't converging to e to the x, kids, but kids, can you see what it kind of sort of looks like? Take a guess. Bam, ba-bam, ba-bam, bam, bam. What is happening now? This infinite series converges, infinite power series converges to what graph? What graph? And notice, right, from here, from 0, 0, the radius of x's where you started to match got larger and larger and larger. What the hee-haw? Now, you've been dealing with sine and cosine for a long time, but you developed sine and cosine under the unit circle from triangle, trig, or whatever. But did you know that they are also infinite polynomials? Polynomials, right? So again, when you, on your calculator, when you hit sine of pi over 3 and you get a decimal, where is the calculator getting that number? I'll tell you where. It's plugging it into a polynomial. It's saying if you want sine of pi over 3, it's putting pi over 3 here, 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 and here, and coming up with a number. And it's not exactly sine of pi over 3, but it's pretty freaking close. Oh my Lanta. This is a famous Taylor series. This series is equal to sine x. Sine x. So I hope you're not going to be too shocked to find out what this one is. What's this one? This is cosine x. And look at the beautiful patterns and the symmetry, right? You knew the graphs were symmetric. Hey, What's the graph of sine x look like? Remember back, what did we talk about when we talked about symmetry? What was true about sine x? What kind of symmetry did it have? It had odd. We called it an odd function because it had point symmetry around the origin. And look at the powers that you have on sine. Math is so freaking cool. What about cosine? What did we talk about when I taught you to graph cosine and kind of describe some of the characteristics? What is cosine? Not an odd function, but since you can fold it across the y-axis, oh crap, we called this an even function. And look at the powers. I mean, life is pretty good. Life is pretty good, and it's pretty awesome that I can see what I'm saying underneath. Pretty cool technology. So, 2 more famous series. Thanks, Brooke. And they are functions you know very well. The first one was e, second was sine, third was cosine. Holy freaking nuts. Now, another reason that you want to know those 3 famous ones. They're known famous Taylor power series because I can ask you to create some other not so famous series without Brooke's formula for building it from scratch. So don't need you. Again, I will teach you next year how to build a power series for any function, not just e, sine, and cosine, right? I just gave you the series here and we discovered them. I'll teach you how to make them next year. But even when I teach you how to make them, sometimes we say, thanks, Brooke, but no, I don't need you because I can use my list of famous series and my algebra knowledge. And instead of writing out the first 5 terms of e to the 2x, of e to the x, e to the composition. Composition, remember in algebra 2, we'd said, hey, if y equals e to the, we'd say, if f of x is equal to e to the x and g of x is equal to 2x, what is f composed with g? And you would say e to the 2x, right? Well, I want you to take Taylor's famous series, e to the x. There it is. And it's not hard to remember. No signs alternate, and you have all the powers, right? You have x to the 0, x to the first, 2, 3, 4, 5, 6, 7, 8, blah, 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 blah. Oh, I don't know why I didn't need to make that all red. And then all the factorials, right? 0 factorial, 1 factorial, 2, 3, 4, la, 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 la. It's not hard to remember that pattern. And why you want to do that is because what if I ask you for the first 5 terms of this series? You don't know how to build it from scratch, but you can do composition. E to the composition is just composition. Hello. How many terms did they ask me for? 1, 2, 3, 4, 5 terms. I'm done. Now, you can clean that up and say 4x squared, right? And 8x cubed and 16x to the 4th. Don't really care. Not my purpose here. Just want you to know that once you have a couple of famous series, you can get a lot of them. And not just by composition. Check this out. Write out the first 5 non-zero terms for not sine x, but x sine x. But if you remember the series for sine x, what was the series for sine x? Sine x, was it even or odd? Think about the graph. Odd. So the sine x series is odds x to the first over 1 factorial. Signs alternate. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. And notice they put non-zero terms here, right? Because there's actually a bunch of terms in between. There's all the even terms are in between, just with a coefficient of 0. But they didn't ask me for the series for sine x. What did they ask me for? Yep. You have an equation. You have an equation. Multiply this side by x and multiply this whole side by x. But how do I do that? Now this I will ask you to clean up. So the series for x sine x looks like this. It messes up my nice clean pattern, but it's because I manipulated it. Right? X to the first times x to the seventh is x to the eighth. Crazy, right? Crazy. Telling you, math is cool. All right. We will do more of this in our next live session.